As a shout out to community colleges in the United States, I also teach at a community college, Northern Virginia Community College, which you don't see up there. Um, we talked about, Roger talked about the Birkhoff polytope, and here you'll see the 6 vertices of B3. And then, of course, if we include the 7th, we have ASM3, which is a 4-dimensional polytope in 9 space. Here we have a complete flow grid. And as you saw, alternating sign matrices can be represented on a flow grid. Note that the internal edges are doubly directed, and each doubly directed internal edges represents 2 oppositely oriented edges. We can make a simple flow grid, and that's just a subgraph of a complete flow graph, and it contains one of each pair of oppositely oriented edges, subject to some restrictions. So again, we're going to use the 6-vertex model, but this time I want you to notice that the arrows on the one all point outward, and the arrows on the negative one all point inwards. So simple flow grids are just a representation of an alternating sign matrix. So you see there's a 1 right here, and right here you see all the arrows pointing out. You see a -1 here, and you see all the arrows pointing inwards. Now, if we combine these 2 simple flow grids, we have an elementary flow grid, which you will see on the right. We have an arrow here pointing left, an arrow here pointing right, which produces a doubly directed edge. Now, I want you to remember this example because I dare not push the back button. And so I want you to remember that these 2 matrices here form this cycle, okay? Now, these 2 matrices, A and B, they're simple flow grids combined to make this elementary flow grid. This is the smallest face containing these 2 vertices, and it is an octahedron. Notice there are 3 doubly directed regions, and as Jessica, the work that Jessica did, we know that this face is going to be 3-dimensional. Notice here that these grid vertices have even degree 4, degree 4, and the rest are all degree 2. There are 12 vertices there. If we add these 4 additional vertices and were to plot these, we would have an octahedron. Now, I want you to remember this example. Whoops, I want you to remember this example as well. See, I'm clicking the back button, getting me into trouble. All right. Now, vertices A and B of a face are estranged in F if there is no proper face of F that contains A and B. Now, on the previous slide, you saw that A and B are estranged. Their combined simple flow grids gives an elementary flow grid, which is the whole face with those 3 regions. And there are other estranged pairs. So we have A and B, C and D, and E and F. So there are 2 things to note. First, that every vertex is estranged from another vertex. And second, that these estranged vertices come in pairs. Now, the original example that I wanted you to note, you remember we took 2 simple flow grids and we got just 1 cycle, one region. We can actually combined simple flow grids B and C then. And they did not give the whole elementary flow grid, so they're not estranged. Now, we can take our elementary flow grid, we can remove the edges which are not doubly directed and undirect the main the remaining edges. And then we have something we're called script G of F. If every vertex of script G of F has even degree and A is any vertex of the face F, then there is a unique vertex B in F such that B is estranged from A and F. If a face F has a vertex of odd degree in script G of F, then no vertex of F has a vertex that is estranged from it. Now, in this example, these three vertices form a triangle face in ASM 3. You notice that script, if you can imagine script G of F from this, you'll see that we have a vertex of odd degree. This is of degree 3. And so the combination of the simple flow grids of any pair of these three vertices do not form the entire face. Or for a triangle or any script G of F, which has a vertex of odd degree, there is no pair of estranged vertices. All right, next concept. Given a grid vertex ij and a face F for which all vertices of script G of F have even degree, A sub ij plus B sub ij over 2 is the same no matter which pair AB of estranged vertices are chosen. So if you choose A and B or C and D or E and F, take those merged matrices, add them, divide by 2, you will get the same matrix, which leads to this proposition: if all vertices of script G of F have even degree, then F is centrally symmetric. The center of F is the matrix A plus B over 2 for some pair of estranged vertices A and B. So again, using our running example, this face, the octahedron, is affinely equivalent to the standard octahedron. And just out of interest, no face of the Birkhoff polytope, B sub n, is combinatorially equivalent to the octahedron. Next concept is that of an ear. An ear of script G of F is a path between vertices of degree 3 or 4 in which every interior vertex has degree 2 or a cycle containing at most one vertex of degree 3 and 4. So we have 3 ears here: this red ear, the blue ear, and the green ear. And if we have F sub 1 contain an F sub 2 faces of ASM sub n, and E is a grid edge in an ear S of script G of F2. If E is not in script G of F of 1, then the orientations in G of F of 1 of the edges of S are determined by the orientation of E. So what do I mean by that? I mean that if we fix edge E, we fix it so that it's pointing to the right, say, then in order to stay within the confines of the 6-vertex model, then the edge to the right of little e must also point to the right, and other edges get fixed also. The same happens in this second example. So if F is a face of ASM sub n and S is an ear of G, we can let X1 be the set of vertices of F with one of the 2 orientations of the edges in S, and we can let X2 be the set of vertices of F with the other orientations of the edges in S. Then the convex hull of X sub 1 and the convex hull of X sub 2 are disjoint faces of F, containing all the vertices for F. So as an example, here's our octahedron. You'll see points A, B, and C. They could be an X1, say, and points D and F, they'll be an X of 2. And the hyperplane containing ABC is parallel to the hyperplane containing DEF. Now, this next slide gives some combinatorial findings. Let's just look at the first and the third. The number of vertices of a D-dimensional face of ASM sub n is at most 2 to the D. And the third one, if a face F of ASM sub n has dimension D greater than or equal to 2, then F has at most 4 times D minus 1 facets. Now, Pfaffenholz listed the 11 combinatorial types of 4-dimensional faces of the Birkhoff polytope. So in my thesis, I found examples of 10 of those 4-dimensional combinatorial types. But there are faces of ASM sub n which are not faces of the Birkhoff polytope and are faces of ASM. 2 of them I've named Polytope X and Polytope Z. Then we have the octahedral prism, the cubical bipyramid, and then ASM sub 3. Now, this table gives all the faces of dimension 2, 3, and 4 found in ASM polytopes. I've used Pfaffenholz's notation, and in this last column, I've listed the lines which correspond to the lines from his paper. So let's take Polytope Z, for example. Excuse me, I apologize to my British audience. I really should be saying Polytope Z, but I've been in the United States far too long. Okay, so S means a tetrahedron, surprisingly. So there are 3 tetrahedra and 3 pyramids, 1 pyramid and 2 octahedra. Anyway, so this is the Schlegel diagram for Polytope X. It's just a 3-dimensional representation of the 4-dimensional polytope. And you can see the outside of this drawing is a facet, which is an octahedron. This is Polytope, the Schlegel diagram for Polytope Z. And Polytope Z has 2 facets, which are octahedra. One of them is this outside KMLSQR that forms an octahedron. And the other has vertices N, O, P, Q, R, and S. But notably, no face of ASM sub n has the combinatorial type of B3. All right, next concept is cycles. A cycle matrix is an n by n matrix whose non-zero entries are in positions corresponding to the corners of a cycle containing the n by n grid graph and alternate between 1 and -1 as one goes around the cycle. Now, in this example, we have a 7 by 7 diamond. You see it's a diamond shape where you have the 1s and -1s. And it's adjacent to permutation matrix P. You'll notice these ones here and here and here are not in P, and they appear in P, and then the 0 gets changed to a 1. Now this matrix C over here, it's kind of a representation of the smallest face that contains D7 and P. If we remove this cycle from D7, it's like obtaining P by walking along the edge of the polytope from vertex D7 to vertex P. And, you know, I can follow this cycle around and get this, and this is just the elementary flow grid of D7. And as I said, it's adjacent to that permutation matrix. So we have a proposition from this: if an ASM A is adjacent to an ASM B in the graph of the ASM polytope, then C equals B minus A is just a cycle matrix. I want to look at the definition of a basic cycle. A cycle K in the doubly directed graph script G of F of face F is a basic cycle for F if it bounds a region of the two connected components script G of F containing K. So here we have an elementary flow grid with two basic cycles, each bounding a region. And if we come back to our running example, the octahedron, you see that we have three basic cycles. And here are their corresponding cycle matrices. Now, we can represent the edges of a polytope by a linear combination of basic cycle matrices. But note that not all linear combinations of basic cycles represent the edges of a polytope. But for each doubly directed region R of G of F, we'll let K of R be the basic cycle that bounds R and is incident to R. So the function K is a bijection from the set of doubly directed regions of F to the set of basic cycles of F. Now, this cycle matrix that we looked at originally is an anti or counterclockwise, for you Americans, cycle. Here we're going from -1 to 1, and if we go from -1 to 1, then we have an anti-clockwise cycle. And in the spirit of Saunders-MacLean for planar graphs, where they were adding with modulo 2, we can just take this cycle and add it to this cycle and add it to this cycle and get that outside cycle that you saw on the very first example I had you remember. Now, these cycle matrices, these basic cycle matrices are linearly independent, and they correspond to, for any face F, the collection of cycle matrices corresponding to the basic cycles of F is a basis for the subspace parallel to F. Now, if an elementary flow grid G has all vertices of its doubly directed graph of even degree, then every doubly directed graph cycle C of G is the elementary flow grid of an edge of F and G. However, one should note that if an elementary flow grid has vertices of odd degree, there may be a doubly directed region that is not an edge of F of G. For example, this picture, I'll just call it a picture, it doesn't represent an edge of F of G. Now, when I was working on my PhD, I was very interested in the path between what I call a left diamond and a right diamond. I'll show you those in a minute, but this elementary flow grid combines the simple flow grids of left D8 and right D8. Now, why was I interested? Because I was very interested in the diameter, and I thought that perhaps if I picked two, like here's a left diamond, here's a right diamond, left D8, right D8. I thought if I picked something that had a lot of negative ones in and they were all in different places, that I'd get the diameter of the graph. Now, what is the diameter of a graph? If you take any pair of points and you find any pair of vertices and find the shortest distance between each one of them, and you take the largest of those smallest distances, just a min-max problem, then that's the diameter. But you can see that if you take out the blue cycle, you'll get to this. If you take out the red cycle, you get to this. And then if you take out the orange cycle and the green cycle from each of those, you get to this. And so the path of from the left diamond to the right diamond is of length 4. Well, that's not what I wanted, but it's a very pretty picture, so I always have to show it. Using CoCalc, we found the diameters of the ASM polytope for n equals 3, it was 2. For 4, it was 2. N equals 5, it was 3. N equals 6, it was 4. And then we had to use some parallel programming. A friend of mine, Emily Evans, did this from BYU. She did this for me and found that this had diameter 4. But if you look at the diameter of the subgraph induced by permutation matrices, you get these same numbers. Now, Emily tells me that we can't do ASM 8 because it'll take 200 years. So I'll be dead by then, so someone else can work on that. Anyway, Belinsky found that the diameter of the Birkhoff polytope is 2. Well, it's 1 for B3, but for greater than, for 4 and up, it's 2, no matter which n you choose. But I'm very interested in finding a formula and proving it for finding the diameter of an ASM polytope. What I do know is that the distance in ASM sub n between two permutation matrices is at most n-1, so this does appear to be linear. Anyway, that's all I have.